2.4 times higher risk. Your risk of developing cognitive impairment is 2.4 times higher if your AHI is elevated, according to a meta-analysis of 69,000 people. And 80% of the people with a clinically significant elevated AHI have never measured it. Not because it is hard to test, not because it is expensive, but because almost no one knows this number exists, including people who sleep 7 or 8 hours a night and feel completely fine. Your AHI is the Apnea-Hypopnea Index, the count of times per hour your airway partially collapses during sleep. And if yours is elevated, it is associated with structural changes to the white matter tracts connecting your prefrontal cortex to your memory systems. Brain changes that accumulate quietly over years while you feel nothing unusual. In the next 10 minutes, you will understand your risk tier, how to measure this at home, and 3 evidence-graded interventions starting at $0. Your AHI counts the number of times per hour your airway partially or fully collapses during sleep, interrupting breathing and dropping blood oxygen. An AHI below 5 is considered normal. Above 15 is where the research literature concentrates its most alarming findings. A population-level epidemiological review estimated that approximately 80% of people with moderate to severe sleep-disordered breathing have never had their AHI measured. Not because they are young, not because they are otherwise healthy, because the most common symptoms, mild morning fatigue, slightly disrupted sleep, are indistinguishable from an ordinary week. The body does not send an alarm, it sends nothing. Everything in this episode is tied to peer-reviewed research. Work with a physician before making any changes to your health protocol. 3 questions this episode will answer. First is, how do you find out your AHI without a hospital sleep study and without a specialist referral? Second, what is actually happening inside the brain during each AHI event, and is any of the structural change reversible? Third, if your AHI is elevated, what does the evidence support doing about it at 3 different budget levels? The answers are more specific and more actionable than most people expect. That 2.4 figure is not a single study's result. It is the OSA specific finding extracted from a 2017 systematic review and meta-analysis in the journal Sleep. 27 studies, 69,000 participants. The overall pooled relative risk for all sleep disorders combined was 1.68. For obstructive sleep-disordered breathing specifically, 2.37. For preclinical Alzheimer's disease detected by biomarker before symptoms appear, 3.78. A prospective cohort published in JAMA followed 298 older women without dementia at baseline and evaluated them cognitively nearly 5 years later. Those with sleep-disordered breathing at baseline were 85% more likely to have developed mild cognitive impairment or dementia at follow-up. This is not a risk confined to people already feeling unwell. The JAMA study enrolled people with no cognitive symptoms. The divergence appeared years later, silently, in people whose only measurable difference was a number they had never been tested for. Here is the finding inside that dataset that changes how you read everything that follows. The JAMA researchers separated 2 components of sleep-disordered breathing: hypoxia, the oxygen drop during each event, and sleep fragmentation, the disrupted architecture. Sleep fragmentation was not significantly associated with cognitive risk. Hypoxia was. That distinction is specific. This is not a quality of sleep problem. This is a cellular oxygen problem, occurring every night, every hour, potentially dozens of times per hour, in a population that has never been tested for it. Here is the leading mechanistic hypothesis for how that oxygen drop translates to structural brain damage, and it involves a biological system most people have never heard of. Animal research established the framework. During sleep in mice, the glymphatic system, a network of perivascular channels that flush metabolic waste from the brain, increased fluid exchange by approximately 60% compared to waking. Amyloid beta, the protein implicated in Alzheimer's pathology, cleared at roughly twice the rate during sleep. The hypothesis: OSA disrupts sleep architecture, fragmenting this nightly clearance process. What does human evidence add? A 2017 experiment published in the journal Brain disrupted slow-wave sleep in 17 healthy adults using acoustic stimulation, without altering total sleep time. Next morning's cerebrospinal fluid showed elevated amyloid beta correlating specifically with slow-wave disruption. Not total sleep lost, not REM, specifically slow wave. Sleep-disordered breathing is among the most consistent disruptors of slow-wave sleep in the research literature. The proposed chain elevated AHI, fragments slow-wave sleep. Slow-wave disruption impairs glymphatic clearance. Impaired clearance accelerates amyloid accumulation. Is biologically coherent and supported across 3 levels of evidence. A longitudinal OSA study is needed for the specific causal sequence. The 3rd level of evidence is the most direct. A 2022 neuroimaging study in Frontiers in Neuroscience measured glymphatic function in 121 people, 59 with confirmed elevated AHI, 62 controls, using diffusion tensor imaging of perivascular space. The Glymphatic Index was measurably lower in the elevated AHI group. A 0.34 degree of impairment correlated with oxygen desaturation severity, not AHI frequency alone. The depth of each oxygen drop. The severity of what happens to your blood oxygen during sleep has a measurable relationship to how effectively your brain clears its waste before you wake up. Elevated AHI is typically framed as a quality of life problem, something that makes you tired, something to address eventually. The structural imaging data proposes a different timeline. A 2008 cross-sectional study published in Sleep used diffusion tensor imaging to evaluate white matter fiber integrity in 110 people. 41 with confirmed elevated AHI, 69 controls. Fractional anisotropy, the measure of white matter, directionality, and integrity, was significantly reduced in the elevated AHI group across multiple regions: the anterior corpus callosum, the cingulate cortex, the fornix, which is the primary output pathway from the hippocampus, and the frontal, parietal, and insular cortices. The pattern is consistent with early-stage axonal injury and demyelination, a limitation the authors flagged directly. Cardiovascular comorbidities, including hypertension, were more prevalent in the OSA group and may contribute independently to these white matter changes. Gray matter changes have also been confirmed across multiple cross-sectional studies, including a multi-site analysis of 120 MRI scans. Early evidence from one small study additionally suggests hippocampal involvement, a finding requiring larger replication before it can be stated with confidence. The corpus callosum, the fornix, the prefrontal and insular cortices. These are the physical infrastructure of memory encoding, attentional control, and executive function. All this morphology data is cross-sectional. These structural changes coexist with elevated AHI. The precise causal timeline is the subject of longitudinal studies currently underway. For those tracking the cardiovascular series, the Wisconsin Sleep Cohort, 709 participants, 4-year follow-up published in the New England Journal of Medicine, showed sleep-disordered breathing independently predicts incident hypertension in a dose-response relationship. AHI above 5 carried nearly 3 times the odds of developing hypertension. The vascular and neurological damage pathways share the same upstream biomarker. So, how do you actually find out your AHI without a hospital sleep study, without a waitlist, and without a specialist referral? 3 options ordered by accessibility. Option 1, free, the Stop Bang questionnaire. 8 yes or no questions: snoring, tiredness, observed apnea, high blood pressure, BMI above 35, age over 50, neck circumference above 40 centimeters, and male gender. A score of 5 or higher carries a high probability of moderate to severe sleep-disordered breathing. 0 cost. 60 seconds. Direct link in the description below. Option 2, approximately $150 one time. Home sleep study. FDA-cleared wearable devices measuring oxygen saturation, airflow, respiratory effort, and body position through a single night at home. They produce an objective AHI estimate with reasonable accuracy for moderate to severe presentations. Multiple telehealth services include physician review and results interpretation within that cost. Option 3, gold standard, in-laboratory polysomnography. Full overnight study with complete EEG, EMG, and respiratory monitoring. If a home device returns a borderline result or the clinical picture is complex, this is the reference standard. Now you know the track. It's time to look at the stack. Here is what to do with your number. The free tier. 3 evidence-supported behavioral modifications, 0 cost. First, lateral sleep positioning. A retrospective analysis of 248 PSG patients found that approximately 57% of those with confirmed elevated AHI had a positional component. Their AHI was more than twice as high lying on their back as on their side. For roughly a quarter of elevated AHI cases, lateral sleep alone normalized AHI below 5. This is not a resolution for severe presentations, but for approximately half of elevated AHI individuals with a positional component, it is a meaningful and immediate modifier. Tennis ball shirt, body pillow, wedge cushion, all free. Second, alcohol elimination before sleep. A 2018 meta-analysis of 14 randomized crossover trials, 422 participants total, found that alcohol increased AHI by an average of 2.33 events per hour across the full study population. In individuals with existing elevated AHI specifically, that increase was 7.10 events per hour, enough to reclassify a mild presentation as moderate. The majority of studies use 2 to 3 standard drinks, within the limits that current public health guidance considers acceptable. The effect on AHI is real at those doses. Third, weight management. A randomized controlled trial published in the BMJ found that in obese men with moderate to severe sleep-disordered breathing, a medically supervised very low-energy diet reduced AHI by 67% over 9 weeks. 17% reaching AHI below 5, Tier 1 evidence, for that specific population. If obesity and elevated AHI coexist, supervised weight reduction belongs in the protocol. If not, the directional relationship remains, but individual response magnitude will vary considerably. $50 per month tier. Mandibular Advancement Device, MAD. A custom or semi-custom intraoral appliance that repositions the lower jaw forward during sleep to maintain airway patency. A 2-year cohort follow-up of a registered RCT compared mandibular advancement device to CPAP in 103 patients with confirmed sleep-disordered breathing. Overall treatment success rates, AHI below 5 or a 50% reduction, were 53% for MAD versus 67% for CPAP at 2 years, a difference that did not reach statistical significance. Nightly compliance was equivalent between groups, where CPAP was significantly superior. AHI normalization, with a median AHI of 0.0 versus 2.0. The evidence-based guidance, MAD, is a viable, non-inferior option for mild to moderate presentations, worth a physician conversation. For AHI above 15, full suppression typically requires CPAP. $200 a month tier, full pathway. Home sleep study, telehealth evaluation, and CPAP if indicated. Several direct-to-consumer sleep medicine services now coordinate all three. Home study, physician interpretation, and device provision often runs under $200 in startup cost, plus device rental of approximately $50 to $150 per month. CPAP requires a physician prescription in the United States. The telehealth pathway makes that accessible without a specialist waitlist. CPAP remains the highest efficacy AHI reduction protocol in the evidence base, particularly for AHI above 15. In one small preliminary study of 17 patients with confirmed sleep apnea, 3 months of CPAP therapy was associated with regional gray matter volume recovery across multiple brain regions, with neuropsychological improvements correlating with anatomical changes. This is a signal, not a definitive finding. It is included because it is the most direct human evidence currently available on structural reversibility, and because it merits attention as the larger studies emerge. Episode 7. Biomarker, Apnea-Hypopnea Index. Retest timeframe, 90 days. Evidence quality rating, 4 stars. Strong meta-analysis and prospective cohort evidence for cognitive risk. Strong DTI evidence for white matter structural change. Emerging human neuroimaging evidence for glymphatic impairment. Preliminary evidence on structural reversibility. A note that belongs in the record. The cognitive risk data comes predominantly from women over 65. The structural imaging data comes predominantly from male patients. Both sexes carry elevated AHI risk, but the research base is not symmetrical, and that context matters when applying these findings to your own situation. The AHI is a number most people have never measured. It is also a number that, at elevated levels, is associated with measurable changes to the white matter tracts connecting the prefrontal cortex to memory systems, changes accumulating quietly across years, while most people notice nothing unusual. The testing pathway is more accessible than almost anyone realizes. The behavioral modifications have published RCT support at zero cost. Was one connection before we close. This episode showed that alcohol worsens AHI acutely through upper airway muscle relaxation in the hours immediately after drinking. What the next episode covers is what alcohol does to the brain through a completely separate mechanism, one that operates independently of sleep, accumulates over years, and is detectable by imaging at dose levels the mainstream conversation currently considers moderate. The neuroscience of ethanol and brain volume loss. Subscribe so you don't miss it.